I thought you were still working on this, calculating and stuff. Okay. So sorry, I guess I should have told them that I was just playing around. But at least I know that we're all talking about Papyrus for real time. So what is Papyrus-RT? Papyrus-RT is Papyrus for real time. There's a little words there, but the project at Eclipse is called Papyrus for real time. It was approved last year, so we're a bit over a year old, and we're still working fine, but everybody calls it Papyrus-RT because real time is very long to say. It's got a whole bunch of things, as you can see here. It's based on Eclipse, of course. It is based also on Papyrus. Of course, it's the modeling platform for what we're doing. It is a, sorry. It is for complex software-intensive cyber-physical system, basically embedded systems especially. It is mainly targeted at reactive systems, so we are not into continuous controls. This is not a competitor to MATLAB. This is really for other areas. It is industrial. It is meant to be industrial grade. We're still building it. When we release it, it will be. It is complete in that it allows you to do everything from modeling, from requirements, use cases, and so forth, into complete code generation in C++ at this point. We are building an ecosystem, and the ecosystem, at the time I first created these slides, were all about PolarSys. But now, since January, there is the Papyrus Industry Consortium with its brand new logo here that really groups a bunch of companies into creating more around Papyrus. The consortium is focused on common objectives, really improving modeling, so model-based engineering. And it's really grouped between 3 different kinds of people. I hope you see this, right? So the most important ones are here. They're the users. Those are the people who look at this and say, yeah, we need a modeling tool, we need open source modeling tools, and we're ready to commit requirements and use cases and usage scenarios to this group who are going to build us a beautiful tool. And we're very happy about that. So they're the most important because they give us all those requirements, give us work, and they also give us money. For a small company, that's fairly important. The other important people are us. I'm part of this little group on the side with the computer coding away, so we're the suppliers. We're the one who look at what the users want. We actually go and build it, we implement it, and we get back to the users and make sure that they get what they want. And at the bottom right, there's another group that's also very, very important, and that's research and academia. So they all have the white little lab coats. And those are people who, they're important for 2 reasons. One, they represent the research part. They represent what is going to come up in the future. And we need to nurture that, and we need to promote that so that we keep advancing the state of the art with regards to modeling, with regards to code generation, with regards to anything around that initiative. But the other aspect there is that it is an incredible opportunity for us to place these open source tools in an environment, either at the undergrad or graduate level, where people will get familiar with the open source tool, and we see that this is a good platform. This is going to be the future. We're basically seeding our future users by making sure that they're all part of this community. Now there's a bunch of technologies in the middle here that we're incorporating into the tool. Eclipse, of course, Papyrus, UML, SysML, EMF Compare, all of these, they're all part of the Eclipse community, and we need to customize these. So I mentioned one thing earlier, that this is a Papyrus platform, and we want to make sure that the difference is understood. For the product line associated with Papyrus, what the Papyrus project is the Papyrus platform. So it is the base on which we're going to build all the Papyrus product line. And we do have multiple Papyrus products defined. Papyrus for real-time, Papyrus-RT is one of them. We also have information management, and we're thinking about things like enterprise architecture, system engineering, or other aspects that we would like to see the whole product line evolve. So what else is Papyrus-RT? Well, at this point, it's Papyrus and UML 2.5. I did mention that we wanted an integration with SysML, so if we have a Papyrus for system engineering, we will certainly want to integrate with that so that we can have traceability between the system engineering part and the software engineering part. I put MARTE there, which is really the real-time spec at the OMG. So this is something we have to look at some point. How can we bring some of the concepts that are part of MARTE, the specification of constraints and things like that, specification of timeliness into UML-RT in the same, into Papyrus-RT in the future. And then what we're building in Papyrus-RT is one very specific modeling language, which is called UML-RT, so UL for real time. There is no formal standard for it. UML-RT comes from a long line, though. Originally, the first version was called ROOM, so the real-time object-oriented methodology, which was implemented in a tool called ObjectTime Developer. ObjectTime got bought by Rational, the tool became Rational Real-Time. Rational got bought by IBM, the tool became Rational Software Architect Real-Time Edition. Same kind of DSL, domain-specific language, that we're bringing forward. It is comprised of the DSL, so profiles and customization of the UI, a code generator, right now for C++, but it's very flexible the way that we've built it. I'm going to talk about that a little bit later. And a runtime for UML-RT, because it does define a certain semantics for the elements that are part of UML-RT. The other thing we were thinking about with regards to Papyrus-RT is that we would like to for it to be a unifying platform. And that, yes, we're implemented UML-RT, but there are 3 very large standards right now implemented by different tools with regards to a real-time version or real-time tools using UML. One of them is XT-UML, so the Executable Translatable UML specification. That has been implemented by Bridgepoint in the past, and that is now being maintained by OneFact, and they couldn't be here at this conference. But OneFact actually proposed a second product in the product line for Papyrus, and there is a Papyrus for XT-UML project that is currently being approved at the foundation. And the third one is RT-UML, so real-time UML, and that's the approach that has been developed for IBM Rhapsody. At this point, we're not quite sure what's going to happen with Rhapsody. I don't know if people have seen, but there's been a lot of divestment from IBM perspective with regards to tooling. But if people in here are using Rhapsody and they think that they want to move, we would like to talk to you. There might be a Papyrus for Rhapsody or Papyrus for RT-UML in the future. We're still in incubation, so we're not quite ready for 1.0 yet, but we're hoping to get there this year. Who is Papyrus-RT? The people who are actually doing the work. So we have, and they're in alphabetical order, not in order of who does the most work. Just wanted to be fair by doing that. We have one person from Alphartech who's helping us with the build, so part of the tooling and the build system. CA list is, of course, the people who are doing Papyrus, so they're the main instigator and they're certainly contributing a lot of work. Eclipse Source is doing a lot of work with EMF Compare. They're the ones who are doing the customization for Papyrus-RT. Ericsson is one of our users. They're contributing requirements, a C++ profile, an intermediate representation, a lot of testing. We were working with Inquiry Lab because we had an intermediate representation. I'm going to talk about the intermediate representation later on. Melina Software, which is really Brand Selleck, who was one of the 3 authors of the ROOM methodology. And Zelixsoft, which is my company, and we're doing everything with the code generation, the runtime, the integration with the CDT. That's all from us. And hopefully we're going to get more people contributing. We do have independent contributors who are not part of Eclipse, so they're not listed here, but they have sent us code patches. So there is an interest outside of these companies. Okay, kind of a history and plan. So we got started in 2014, and then we've got a whole bunch of release. We actually were hoping to release 1.0 in this month. Lately, we've looked at all of that, and we decided that we did not have the quality. And because we're an agile development team, well, we did not meet the requirements of our minimal viable product. So we're basically going to keep working until we actually meet the sufficiency for our MVP. So this schedule is no longer valid. I've got a new one that we actually approved kind of on Monday during a meeting. So I'll have to update these slides, and I'll update the slide before I actually post it so that people will see what our plan looks like in the future. So at this point, our goal is to have a 1.0 in December. So basically, Neon.2. Architectural overview. We're based on Papyrus, so we have a whole bunch of things from Papyrus, and then we add, again, I'm going to reiterate thing, but it's a nicer diagram. The DSL, everything that has to do with user experience, so making sure that we have a very good user experience with regards to capsules, protocols, state machines, hierarchical structure, hierarchical state machines, and the modeling experience in general. Papyrus was not exactly known for its usability in the past, so we're trying to resolve that, both on the Papyrus level, but also especially on tools that are implemented on top of Papyrus. We're also doing a migration from RSA Real-Time Edition, because we do have customers, we have users who are interested in moving their models to Papyrus Real-Time. And we have Code Generator, which is a multi-step code generator. You can think of it a bit as an MDA approach with regards to that. And we have the Runtime Service Library, which is C++ extensible. And we have another aspect which we call hybrid modeling, which is not yet ready. Not even to really demonstrate at this point. We're hoping we'll get better demonstration by September. But basically, you'd be able to create your model either in the textual format or a graphical format and have an interchange between the two. So you could create your structure in text because it's very easy to create structure in text and it makes sense. It'll create the model for you, the graphical model. But if you want to start creating hierarchical state machines, it's actually easier to create a hierarchical state machine graphically than it is to create it in text. It's easier to follow. So it's basically a mix of both worlds, and it addresses kind of the inner loop of development when you start modeling. So it's certainly something that's of interest to a bunch of people. So the architecture of the code generator, I already talked about how this was kind of an MDA approach. So we're basically got multiple levels defined here, so platform-specific layers, so to speak. So we're starting with the UML-RT model, which is really a UML model with a profile applied. And what we're doing is multiple translations. So we're translating the model at this here into an XT UML-RT model. We had created a meta model for this whole thing that had both UML-RT and XT UML components in it, so we can actually, using that, translate then from this model into a C++ model, and from the C++ model, generate the CDT project where everything is going to be built. And that allows us more flexibility, because if you want to add a meta model here, well, the rest is probably going to work pretty good. If you can change a C++ model by a Java model if you wanted to, and you'd still get the chain that actually works properly, as long as you respect the interfaces that we have defined. Most of our stuff is implemented in Java and in Extend. So yes, we are reusing Eclipse technology. It does support incremental generation, and we do have a force regenerate just in case things go wrong. And at this point, we're targeting with the code generator, we're generating C++03 code. And the reason for using an older version of C++ is there are still a lot of embedded system companies that are on older versions of C++ because they are running real-time operating systems where this is the only version that's available. So if you can compile on C++03, you'll be able to use a more modern compiler later on anyway. The architecture of the code generator, and that's a bit more complicated, but we do have models of parts of what we've done in UML-RT, in Papyrus-RT, so we do have a model for the code generator. And that's the model that's also being used to drive the extent transformation. So there's the code generator itself, and we see that it goes and uses a whole bunch of other segments. So we have groups. And again, we've done that so that it's it's all components. So if you wanted to change, for example, the way you wanted to, the way you want to generate a protocol, well, you can just change that class or overload that class, inherit from it, and override some methods, and you'd still be able to just go for it, right? So you can plug and play other things, and it makes the whole approach very modular. One of the things that I probably forgot to mention is that, yes, we want to meet the needed users, but one of the users that we have defined as part of the work to define Papyrus for real-time is that we do have a toolsmith users. Actually, we have multiple toolsmith users depending on which areas of this is of interest. And we made sure that, for example, if you have a code generator toolsmith, which is one of the actors that we've got, there is something that they can do. And I can show the use case model if anybody's interested at some point, and where we define all of that. The architecture of the runtime, because our runtime is C++, it's basically all C++ and make files. So we do have an architecture where it's very well defined what can be changed. So for example, we have OS-specific makefile fragments. So if you change one of the source file from Linux or Windows, you can run one of these make files and it'll go get the information from the right folder automatically. So the main make file will determine your platform, your compiler, and then you'll go and fetch the right source files so that you can actually have the customization. So running on Linux or Windows or Mac OS, we're going to be able to do that with just providing new implementation of certain functions. For example, threads. The thread implementation on Linux and Windows and Mac OS are all different, so we want to make sure that we can abstract that out. Semaphores, and there's a whole bunch of others, right? Without having to replace files. So it's just creating new files and making sure that your make files do it correctly. And the whole make system that we're going to be using is actually an external contribution. I talked a bit about hybrid textual graphical modeling, and at this point this is still a bit of a research project. And I explained what we wanted there. So the graphical representation is certainly good for a whole bunch of things. If you want to see the relationships between the elements in your model, well, there's having a graph where you've got classes or capsules and being able to really see the relationship between them is very quickly, you can very quickly understand what the model is about. So in those cases, it's very good. Other cases like editing hierarchical state machines with deeply nested hierarchical state machine is typically easier to do in a graphical way. But textual representation also has its good points, where model structure is very quick to do in textual. It can be modified a lot quicker. So the runtime is very often very quicker. And the other advantage is the whole diff merge area, where it's a lot easier to compare and merge a textual language than it is to start looking at all the various graphical information that is stored in the model. It also helps, but that is only true if you've got a good layout mechanism in the end. You have to have a layout mechanism where it actually gets back closer what you had decided. So if you decide to move a class or a capsule somewhere else, it needs to be able to keep that kind of information so that your graphics don't change all the time. So there's a lot of research to be done about that, and we do have a European project that has been approved with regards to that. So we're hoping that we'll get something very good going forward. An overview of the transformation, another graphic. So from graphical only, that's the way we're doing it. So that's the way that if you use the tool right now, it's going to look at. So basically, you're going to the profile to an instance model, model transformation to code generation. And if you look at the textual, where you're going more on the textual side, you're going back on the textual side, which is around our instance model that conforms to our E-core. So that's pretty much it. That's what it looks like, but I'm going to skip that slide because I prefer to show the model. It's just that this one is scaled properly. The model I have to move around a lot more. That's the example of the textual model. So capsule and the textual language has changed since then. So we define a capsule. We can define a state machine in it. We have ports that are associated with it. So conjugated port here. And we have a top that contains elements of the other two with connectors. Okay, any questions before I start the demo? I know I've said a whole bunch of things and I don't want to miss my deadline.
I guess quick question because I have to be early.
Yeah.
The code generation, how easy is it to hook into there, and is it possible to trace back from the C++ model to the original UML model?
So if you know extend, it's easy.
All right, so it's an extend.
So yeah, it's all in extend. So I mean, it's well structured, and you saw the class diagram. So all the dependencies are known. So if you know extend, you'll be able to go in there and replace whatever is in there. So that should be fairly easy. If you don't know extend, well, learn extend first.
I guess if you hook into there, you hook into the code generation from the C++ model. So.
Yeah. So that there's a transformation to the meta model, and then there's a code generation afterward that.
Right.
Okay.
So I guess sometimes it's important to get the context if you just have the
yes.
C++ model. So is there a way to trace back to the UML model from the C++ model?
Yes, there is, with some caveat. From the UML model to the intermediate model, definitely all the links are there. It's very easy to, and the methods are there to actually go back. Not a problem. Right now, we don't store anything in the generated C++ code, but we are keeping some information because of the text, because we do need to come back at some point. We knew that we were going to come back at some point. I'll have to check with the developer exactly where we are with keeping those indexes. But yes, the intent is that we will have complete traceability back and forth, because from our point of view also, one of the things that we need to implement is a model level debugger, so that you are working at the model with the model itself. Well, if I create a breakpoint in the model, I need to create the breakpoint in the C++ code, but when the breakpoint is hit, I need to tell the model. So I need bidirectional traceability in order to do that. And the same thing also for observability, in that if I want to put an observation point in the C++ code telling me, hey, this variable now has changed value, well, I need the same kind of connectivity between the two so that at runtime I can get that information. Which state am I in, kind of thing. So yes, we will have all that information stored. Where we are right now with regards to this whole traceability, I'm not sure. You're welcome. Any other question? Okay, the other thing is we're going to use the rover to demonstrate things. That is a picture of Mars. But we're going on neon, so I have to find something neon related. I've got a bunch of links that you can go and have a look at. It'll be in the presentation. There's a bunch of stuff that you can read. Again, as much as possible, well, actually anything that has to do with the project themselves is going to have a link and is going to be accessible, period. This is completely open source, and we're going to be completely open about that. So let's move to Eclipse. And what I want to do is start with looking at a more complex system, just so that you can see what it looks like when it's more complicated. Why is it showing me this? Okay, sorry about that. This was supposed to bring me to the right place, but there's a link that's wrong, so And working at this resolution is not fun. There we go. Okay. So the computer system, it's basically a model of a computer system, and I'm bringing this up because it's got all the different elements of UML-RT. So by default, all these blocks here are capsules, and there you know they are capsule because it's got the little decorator in the top right. The capsule only communicate through ports. So those little boxes are ports, and the color tells you whether they're directly implementing the protocol or they're implementing the reverse of a protocol. So to port to be connected, the input must be the output must be the input. So that's the conjugation that we're using. A protocol is basically a set of in signal and out signals. So I'll find a protocol really quickly just to show you. And you'll see that the Model Explorer here is not the Eclipse, the Papyrus Model Explorer, so it has been tailored. So protocol is a first level instance in UML-RT, so that's why we've got that. So it's got out messages and it's got in messages, basically. The capsules that have line like that are optional, so we have to create them dynamically. And I've got a capsule here that's a plugin, so I can actually import a capsule into another context. Basically a reference, but a capsule is more complex. A capsule, by the way, implements their own logical thread of control, typically. And that means they also have run-to-completion semantics. So if they receive a message, they completely process the message before accepting another message. So it's a messaging-based application. We also have service ports, which are shown as little circles. You can be either a service provider or a service consumer. So this is a service access point, and it's accessing some of the runtime services. So all the runtime services in UML-RT are expressed as a service access point. So they are expressed by a protocol. In this case, there's a timing, and we have a frame protocol, the frame being all the dynamic incarnations of model elements. And then I can do things like interesting patterns in there. I can manage resources, and I've got communication that can occur through all of these. And this is a very complex model because I'm importing stuff in different contexts. So to explain how that works, it's a lot easier for me to go with a much simpler model. And that's the ping pong model. And hopefully, and this one worked. So ping pong model, has anybody not seen a ping pong model? Yeah, that's what I thought. So basically there's a pinger, there's a ponger, pinger starts the game, ponger just returns the ball. Very easy. So this is all message passing. So in this case, I've got a pinger and I've got a ponger, and pinger will send a message to ponger, and ponger will reply, but what's wrong with this diagram? Pascal? Yeah, I don't have a channel by which the messages can be sent. So yeah, I've got the ports, but I need to tell them, well, it has to go through something. So I do miss a connector between the two. So again, the nodes is very simple. There's not a lot of things to do there, but I can just add a connector. And as you can see, the UI is still not perfect because I'm not supposed to see these nice little things here, and we're going to make those disappear because they're not adding anything to the diagram. Well, okay, let's have a look at pinger then. So you'll see that we've built navigability in there. I just double-clicked on the capsule. It shows me what's inside the capsule, so the structure of the capsule. Right now, this one doesn't have much, but I could also double-click on the capsule instance, and then I'll get the state machine that's associated with it. We don't yet have the return, so I should have a menu item, a command here that I can go back to the structure, but we don't have that implemented yet. So UML-RT, it's all state machines. There it goes into the running state in this case for pinger, and I'm setting a timer. As I get into that state, I'm setting a timer, and when it times out, well, as part of the timeout, I'm going to send a ping and then wait for the pong to return. Now the ping in here, what I can do is I can generate the C code for that. I guess it's already. Did I mention it wasn't quite finished yet? Normally I have all of these open. Okay. I'm going to go back to Pinger state machine. And well, actually I'm going to go to Ponger state machine first. And because Ponger I don't have code in there, so I didn't generate the code, which is why I didn't open the CDT project. So I do have a trigger. Oh yeah, for a transition, you do need a trigger, and a trigger defines the port and the message that is going to trigger that transition. So in this case, the port is Pong port, and the message is on ping. So when that message is received, then that transition can be taken. And I think I'm running out of time right now. I think I'm out of time. Yeah. We started a bit late. If anybody wants to see this, we can sit out outside. If you want, I can record a complete demo and send it out and put it with my presentation. And if there are any questions, I don't want to take too much time of next speaker. Is next speaker here? Yeah, so sorry.